All right, I wanted to make sure that I actually went through the solution of this problem because it was a little bit of a challenge for people, and it's a bit of a different approach than what we've been doing for other problems. So we have this mass that's swinging around in a circle, and the idea is that if it goes too slowly, it's going to spiral into the center of the table, and this mass, big M, is going to drop. And we want to know the minimum speed that M needs to go in order to hold up big M. And that's the idea. So let's actually start with some free body diagrams. First, for little m, we're going to have the tension on it that keeps it in a circle. We've got the normal force on it because it's resting on a table, and we have its weight. And then for big M, we've got the tension holding it up, and we've got the weight of big M wanting to drag it down. And to be clear, the tension that makes little m move in a circle is the same tension that's holding big M up. And what we're going to do is we're going to express all of this using equations. So the tension that makes little m accelerate in a circle, that's me writing down the unbalanced forces equation horizontally, is the same as the tension that fights the downward gravitational force, or the weight of big M. And those two forces balance because big M is kept supported in the air at rest. Now there is another equation we can write down, which is that the normal force on little m fights the weight of little m, and those forces actually balance. So we actually learn that the normal force acting on the puck is equal to the weight for this puck. This equation is true, but it's not helpful. So I wrote it down just so you know where all the forces have been accounted for, but we're not going to use this. Continuing on, we are actually now going to plug in every number that we possibly can. So I know the tension equals 0.021. Now for AC, I'm going to actually substitute the formula v squared divided by the radius. And that's going to be v squared divided by, and the radius is 20 centimeters, or 0.2 meters. In fact, I'm just going to change that right here to 0.2 meters. And here we have the tension minus, and now I'm going to substitute mg for weight, and they balance. Now I'm going to plug in numbers, so the tension equals the 0.55, careful, this is capital M, times g, which is 10. So my tension is 5.5 newtons of force. I can go ahead and substitute that into here, so I'll get 5.5 equals 0.021 v squared divided by 0.2. And I can go ahead and actually, I'm going to simplify this and solve for v. And when I do that, what I'm going to get is v is 7.24 meters per second. And that's the answer to this problem.